So as I said, I want to use this last session for an overall summary of what we did. And of course, the main focus will be elliptic curves, but I also want to talk a little bit about groups and fields, so that you will, I mean, to refresh your memory, and also to give you something to, I mean, kind of the main highlights of each topic that I think is good for you to take with you and to remember. So we started with groups, and here the focus was abelian groups. And for abelian groups, we had what is called the classification, which means that every finite abelian group G is isomorphic to well, a product of cyclic groups, but it has two ways to write it. So one, I'd say, finite of order n. So one way to write this isomorphism is integers modulo p to the e, p1 to the e1, direct sum integers pk to the ek, where it is the product of the pi to the ai are the prime decomposition of n. And the second isomorphism is written like this. Wait, just why don't make a. So it's basically integers modulo n1, direct sum integers modulo n l, such that for any I bigger equal to 1 and smaller equal, well, smaller than L, Ni divides Ni plus 1. And we use both of these forms, kind of canonical forms for abelian groups, to reason about abelian groups that we come across, mainly abelian groups that appear as elliptic curves. And then we went to fields, and here as well we had a classification result which means that for any prime p and a positive integer n, there exists a field which is denoted f p to the n with p to the n elements. And any other field with p to the n elements is isomorphic to this field, fp to the n. So this is a very strong uniqueness property, and using this, we can define concretely what is called the algebraic closure. So the algebraic closure, I take, well, there is a small fact that if n divides m, then we have a subfield inclusion or a field extension fp to the n as a subfield of fp to the m. So so what we can do now is we start with fp, and then we go to, for example, fp square. And now if we want to keep a field extension, then we need, for example, fp 4 and so on. And we can take the union of all this. So I take union of fp of 2 to the k, and then I'm guaranteed that I have a field extension in each step. And this I call the algebraic closure of fp. And it's also, as a set, you can simply think about it as just the union of all fp to the n, where n is bigger or equal to 1. But the field structure on fp bar requires that that you talk about field extensions, so you need a tower like this. And fp bar has this property that every polynomial over fp bar splits to linear factors. Okay, so that's groups and fields, the takeaway from these sections, and then we move to elliptic curves. So we have this group law on the elliptic curve that is inspired by this geometric picture over the real numbers, that you take 2 points, you draw the line P and Q, and this is say P star Q, and this is called P plus Q. And the formulas can be presented in a purely algebraic way, and that's why they are meaningful over FP. over finite fields. And this we didn't prove, but in fact it follows from something that we proved in later sessions, that E over K, if for any field K, the K rational points is an abelian group. And of course, if we take this tower that we had of fields before, then I can apply, and let's say E is defined over Fp, then I can take the Fp rational points, and this would be a subgroup of the Fp square rational points. And all of it is going to be a subgroup of E over Fp bar. So the Fp bar rational points of E. So this is a tower of groups. Then we went into this business of rational maps. So I mean, we want to be able to understand maps from the algebra or geometric objects that we care about, in this case, this elliptic curve, into the field. But the maps that we want to consider are polynomials or quotients of polynomials, in fact. So we do some algebraic construction, namely, we take the ring of polynomials in two variables, and we quotient by it's in fact an ideal. I didn't talk about ideals in the course, but we quotient out by the relation, let's say y squared minus x cubed minus ax minus b equals 0. So it's like we take polynomials and declare that a certain polynomial is going to be 0. And this is analogous to you take, let's say, Fp. You take polynomials in Fp, and you mod out by some given polynomial phi. And this means that you look at the polynomials over Fp with one variable, and whenever you do operation like addition and multiplication, you do as you are used to, or like operations on polynomials, but you do modulo phi. It's like, and this in turn is analogous to what we do in integers, right? I mean, when we do integers modulo n, we do addition and multiplication as we are used to of integers, and then we take modulo n. So here I can define this I call polynomials over E. Okay, it's like polynomials in which I identify the specific polynomial that defines the elliptic curve. And already here, I have, polynomials over E, I have the algebraic description. So a polynomial over E is going to be some fxy that is a polynomial over K. But if I add two of them, or let's say I multiply two of them, then basically I can replace all the power of what, well, I guess in polynomials over E, I have a canonical form. Which means that I take fxy and I replace all the powers of y by x cubed plus ax plus b. And then I get some polynomial in the x variable plus y times another polynomial in the x variable. And I can think about polynomials over E as just elements of this form. And I do addition, multiplication, and then the reduction modulo this polynomial is simply replacing all the instances of y squared by x cubed plus ax plus b. So this is the algebraic description, but it's not just an algebraic description. I can actually think of a polynomial over E as a function. Namely, I take the collection of all k rational points and I map it to the field k. In fact, it's not exactly the field k, because I might, here I have the finite points plus the point at infinity. So, obviously what I want to do, if I have such an f, I want to say that f of p, if p is some x0, y0, then f of p is f of x0, y0. And this is always in k unless p is equal to O. So when p is equal to O, I say that f of p is infinity. And this we called the projective line. So a polynomial over E is basically an algebraic creature, but it induces an actual function. Now, not every function from E of k to the projective line is a polynomial over E. But obviously, like you can do many non-polynomial functions, but this algebraic creature that we care about always induce a function like so. Is this okay now? Are you following?
Yes, thank you.
Okay. So that's polynomials, and the intuition, let's say again, we go back over R. I have this this curve E of R, and if I have some polynomial fxy, it defines a map. Typically fxy defines a map from R squared to R. Right? You take a point x0, y0, and you substitute in F. But when I take F in this ring of polynomials over E, I think of F as restricted to only the points on E. And then I do whatever F does as a polynomial. I just substitute in the polynomial. So a polynomial over E is like a function from the green part to the green part here. This is like R. And of course, the same thing applies to any field. But then I don't have like a nice picture to draw. And then we can say, okay, we anyway start getting infinity when we talk about polynomials over E. This because we have this point at infinity. So we might as well talk about quotients of polynomial. One motivation you can say I have this guy polynomials over E. What is it as an algebraic structure? It's a ring. A ring means that I don't have inverses to every element. I mean, some elements have inverses, but some elements do not have inverses, multiplicative inverses. So I would like to embed this ring into a field, kind of a minimal field. So the natural way to do is to imitate the construction of the rational numbers. I mean, what do I do with the integers? I don't have multiplicative inverse for n, so I look at the collection of all fractions, and in the collection of all fractions, the element n will have an inverse 1 over n. So here as well, I can do this construction, and that's why it's called rational functions. So rational functions, let's call it rational of E. We had a better notation for this. This is like K of E. This is, I take quotients of F and G such that F and G are polynomials over E. So they already are need to come in, either they come in this canonical form, or I need to think about them as equivalence classes, such that G is non-zero, is not the zero polynomial. Just like irrational numbers, I don't allow the numerator to be zero. And here I have basically an equivalence relation, so I write it like this, where the equivalence relation is that F over G is equivalent to, I don't know, H over K, if and only if Fk is equal to GH. But equal means in polynomials over E. Okay, and just like in polynomials, we have the algebraic description of rational functions, but we also have, you can think of them as a geometric function. I mean, if R is a rational map, a rational function. We have a function from the collection of all k rational points to the projective line that as with polynomials, I mean, I take a point P and I do R of P. So if P is equal to x0, y0, then I do R of P. This is just substituting x0, y0 in the polynomial, or in the quotient of polynomials R. And sometimes I get infinity, but I anyway had to introduce infinity as a possible value of polynomials over E, so I don't care that much. So again, we have this algebraic description. It's like a rational function on E is a quotient of polynomial, but it also induces an actual function. So we can think about it, and eventually we want sometimes to think about it as a function because we want to compose. Like, let's say I have some map between the k rational points to the k rational points. This could be multiplication by n. I would like to compose the two things. And so this point of view of a function is important. Is this okay? So now there is this a business of zeros and poles. So we have a notion, I mean, the set of zeros of R is the collection of all points in E of K such that R of P is equal to 0. And the poles of R are the collection of all points P such that R of P is equal to infinity. And we started to unravel a very strong symmetry property of rational functions that, well, I mean, it has several implications, but the bottom line implication is that a rational function on an elliptic curve is determined up to a product by a constant by the set of zeros and the set of poles if you know the multiplicities of these zeros and poles. And so we went into a detour of trying to define what is the multiplicity of a zero or a pole of a rational function. This is this business of uniformizers. So a uniformizer, let me see if I remember the definition. It's say R is a rational function, and P is the point on the curve. Let's say we only care about zeros and poles, so such that a P belongs to the set of zeros and poles of R. And now I want to define what is the multiplicity of P with respect to R, or what is the multiplicity of R at P. So I say if there exists a rational function U such that one, U at P is 0, and two, R can be expressed as U to some D times S, where S is another rational function that doesn't take funny values at P. So it's not 0 and not infinity. Then U is a uniformizer. And D is the multiplicity of R at P. And we had a theorem that uniformizers always exist. They exist. You pick a point. I need to say, to be more precise, I need to remove the quantification of rational points. Of rational functions. So I want to say, suppose you are given a point P. If there exists U such that for any rational function R, you can express, let me put it here. So if there exists a rational function U that is being nullified at P, and for every other rational function R, R can be written as U to the D times S, where S does not have a 0 or a pole at P. Then we say that U is a uniformizer at P. And in this case, for this a specific R that has a specific D, we say that D is the multiplicity of R at P. And this is, before the theory maybe, this is analogous to what we do with in polynomials in one variables. So I mean, if I have fx is a polynomial in one variable over a field, and x0 is a 0 of f, then how do I determine the multiplicity of x0 as a 0 of f? I say I can write f as x minus x0 to the d times g of x, where g of x0 is non-zero, right? So the d that allows me to do that is then the multiplicity of R at x0 sorry, of f at x0 is defined to be this number d. And the definition of uniformizer is supposed to imitate this procedure, but because we are talking about polynomials in two variables, it's a bit harder. So we need, I mean, here, polynomials in one variable, the uniformizer is always of the form x minus x0 for some x0. But in polynomials in two variables, we have a more difficult time. So we have this definition of a uniformizer. And there is a theorem that for any p, there exists a uniformizer at p. The terminology uniformizer is because of this quantification here. That is, a uniformizer is some rational function that is suitable to, I mean, with which I can extract the zero or a pole of any rational function R. So in a kind of a uniform manner. Is this okay? Okay. So uniformizers at P always exist. They have, I forgot so we have three cases. I mean, we have it at a point that is not of order 2. P does not belong to E of 2 or infinity. Then I think the uniformizer was, I mean, let's say P is AB. Then the uniformizer was X minus A. And then if P is a point of order 2, but not the point at infinity, I forgot what was the form. Let's see.
Maybe it was X over A.
I think it's Y. So UXY is just Y. It's not AB because it's actually A0. A point of order 2 has to be of the form A0, right? And then in the third case, if P is equal to O, then U needs to be UXY is X over Y. And this is one possible choice of uniformizers. You can choose others. I mean, first you can multiply by any constant, it will stay a uniformizer. But you have other choices as well. But the important thing is that in addition, D is uniquely determined. So for any rational function, R, the D or D of R is uniquely determined for any rational function and any point. Well, so all in all, we have if R is a rational function, we define D. We define if R is a rational function and P is some point on the curve, we define the order of R at P to be this number D. And this is well defined. And for this, it would follow from the definition if P does not belong to zeros or poles, then R of P, the order of R at P is going to be 0. If P is a 0 of R, then the order of P at R is positive. And if it is a pole, of R, then the order of P at R is negative. Questions so far? You can also ask for things I didn't talk about that you want to cover. Now you specifically wanted to know a bit more, to refresh your memory on this part?
No, but I think this part is fine, but thanks. Yeah, so far so good.
Okay, so then we went into this this business of trying to show the symmetry of zeros and poles of a rational function. The main theorem here is that if you take a rational function and you take the sum of all orders of points with respect to R, so I run over all points of E. There is a prerequisite result that we need to know, that the number of zeros and poles of a rational function is always a finite set. So I can always take this sum. For points that are not zeros or pole, the order of this point with respect to R is 0. So it's a sum with only finitely many non-zero summands. So I can take this sum, it's a finite sum, and the theorem says that it's always 0. This is a very, in my opinion, it's a very surprising result. If you don't know what is going on, and this means that there is a very powerful symmetry, right? It's like I have a rational function, I don't know anything about it. I look at the number of poles and the number of zeros, and I count each with their multiplicity, and I get 0. And so this will eventually be one of the pillars that we use in order to construct the well pairing and so on. But to show this, you can first go to polynomials over. So let's say a stepping stone. You take polynomials, let's say a polynomial over E. This polynomial, I kind of know, I mean, what is the possible pole of a polynomial over E? I claim that the only pole of a polynomial is the point at infinity. This is because, I mean, what is a polynomial? This f is like, I can put it in canonical form, for example. And I need to find a point P x0, y0, such that if I substitute it in f, I get infinity. Well, if I take x0 and y0, I mean, if P is a finite point, then x0 and y0 are element in the field, and I substitute it into a polynomial, I always get just another element in the field, not infinity. So the only way I can get infinity is if I substitute in a polynomial, I substitute the point at infinity, which I remind you, it's useful in this part of the course to think about the point at infinity as heuristically as being infinity comma infinity. And then it's immediately clear that if you substitute infinity comma infinity in f, you get infinity. So O is a pole of f, and it's the only pole. But in fact, we had like a proposition that showed that the order of a polynomial at the point at infinity, which we know is a pole, is exactly minus the degree of f. The degree of f, this I skipped, but we had like we had a notion of degree that is special for polynomials over E, because in polynomials over E, I have this relation y squared minus x cubed minus ax minus b equals 0. And this relation, if I want to keep a consistent way of degree, then I need to declare, let's say there are many options. I need to keep the proportion between x and y, the degree of x and the degree of y, to be 2/3. So I take the natural choice is that the degree of y is 3 and the degree of x is 2. Okay, and then this equation is also compatible with degree. I mean the degree. Let's say I move this equation. I have y equals y squared equals x cubed plus ax plus b. Then I need that this will also be equation of degrees. But if you look at this choice, I mean, y, if I take the degree of y to be 3 and that of x to be 2, then I also have equality of degrees. So that's the motivation. But then with this notion of degree of a polynomial, I find out that the multiplicity of the unique pole of any polynomial is minus the degree of this polynomial. And the multiplicity of all the zeros is going to be the sum. I mean, is going to be, if you sum all the multiplicities of the zeros, I guess I can write it, the sum of all order of P at F, where P is a zero of F, this equals to the degree of F. This is like in ordinary one variable polynomials. I mean, so altogether we get the big result that we want. We get it for polynomials. I mean, the sum of all multiplicities of zeros and poles is, at least in the case of a polynomial, is zero. So the sum of all order P R P in E, not R, F, is going to be zero. But then, I mean, what is a rational function? It's just a quotient of polynomials. So once you have this stepping stone, you can, it's not hard to prove the claim for a general rational function. I guess now would be a good time for a break, but do you have questions? Requests for the session, the part after the break?
I would love to revisit divisors.
Yes.
Because it is still, for me, something that is like a bit of foreign thing.
Okay, yeah, sure. We will definitely get to divisors. You see, in one hour we covered like half the course or something.
Yeah, this is very useful. So thank you very much. Yes.
Okay. So see you soon.
Cool.
Okay, can we start again? So just a small correction. Everything that I said here about this big theorem and the stepping stone is assuming that K is algebraically closed. Otherwise, this symmetry doesn't quite hold. And we had a few examples. You can cook easy examples with points of order 2, because you know that if I don't go to the algebraic closure, I don't have all the points of order 2. Like there should be always 4 points of order 2, and I don't always have them if I'm not algebraically closed. So this symmetry really assumes that K is algebraically closed, and otherwise, you know, you can have many examples that do not satisfy it. So, and this brings us to divisors. I mean, what I want to do is I take a rational function, and I mean, we already saw that it's very useful to look at the zeros and the poles of a rational function, and also their multiplicity. So to every rational function, I can associate something. I will eventually, a posteriori, I will call it, or let's say, I can already call it now, the divisor of R, which is, I take the sum over all points in the curve of the order of R at P times some formal instance of the point P. It's like this bracket P, you can think about it as like a variable, X or XP maybe. It means that I only want to record I mean, for every point on the curve, what is the multiplicity of this point with respect to R? And obviously, like if K is algebraically closed, this was another small proposition. For K algebraically closed, E of K is infinite. So if I want to cover also the case of K algebraically closed, I need to know that this sum is always finite. But it's okay, because we know that a rational function can only have finitely many zeros and poles over E. And so this sum has finitely many non-zero elements. And the rest, I mean, whenever I have 0 times P, I just ignore it. I mean, I just treat it as 0. And of course, if K is algebraically closed, that then we have, so if K is algebraically closed, then we know that the sum of all multiplicities of zeros and poles in P is going to be 0. But K is not necessarily algebraically closed. So we would like to extend the view of what is a divisor to also these cases in which K is not algebraically closed. We don't have this symmetry, and therefore it makes sense to abstract a little bit and talk about divisors as a formal artifact. So a divisor over E is a formal sum D is equal to sum NP bracket P, where P runs over all the points on the curve. And I have two conditions. One, only finitely many NPs are different than 0. And each NP, for each P, NP is an integer. And you see the collection of all divisors is denoted as div E, or div E over K, all divisors. And within this collection of all divisors, I have a sub. Okay, so before I get to that, this collection of all divisors is naturally an abelian group. Why? Because if I have a formal sum, D is a sum NP bracket P, and I have D prime, which is sum NP prime P. Then I can sum them, I can sum the coefficients. D plus D prime is the sum of NP plus NP prime. I mean, at the formal instance of P, bracket P, I do NP plus NP prime. And I run over all P. This is again a finite sum because each of these guys is a finite sum. I mean, so for example, D could be, let's say, 2 times O minus 3 times P. And D prime could be minus 3O plus 4Q. I mean, just formal sums that have each of them has only finitely many expressions that are non-zero. And if you want to add them together, well, you know what to do. You get, so D plus D prime is minus O minus 3P plus 4Q. Okay, so it's important to distinguish the. I mean, a divisor is like a formal expression that is an abstraction of what we eventually want to capture. I mean, eventually we want to capture zeros and poles of rational functions, but we extend the view to all formal sums, because one of the main reasons is that this is an abelian group. I mean, if I don't extend it to this generality, I don't necessarily have inverses. Here, the inverses are very easy. I mean, what is minus d? Minus d is sum. You just do minus over the coefficients. But if you only considered divisors that come from rational functions, we don't know, at least a priori, that we have the inverse of a given divisor like this. So within the set, the group of all divisors of E, there is the so-called principal divisors. Principal divisors are divisors of the form div R for some R. Maybe, you know, a priori, again, if there could be more than one rational function that that have the same divisor. So if you give me a specific divisor like this, a priori, there could be many rational functions that have this divisor. In this case, this divisor cannot possibly be a principal divisor. Why? Anybody? This divisor D, I'm saying this divisor D cannot come from a rational function.
Because the sum of its coefficients is not zero.
Is not zero. So in order to correct it, I would need, I mean, if I want a D to be a principal divisor, to have a chance to be a principal divisor, I would need let's say the double prime. I could do 3O minus 3P. And this could be potentially a principal divisor, but there is a second condition that we will talk about soon that really is necessary for a divisor to be principal divisor, namely that if you remove the brackets and you do the sum in the elliptic curve, that is, you do 3 times O minus 3P, you get O. Okay? So, and this, I will come back to it soon, but this is the second condition of what does it mean to be a principal divisor? Or, I mean, it's like an equivalent, a characterization of principal divisors. So here, in order for D prime to be a principal divisor, P needs to be a point of order 3. That is, 3 times P needs to be O. Okay? So that's kind of a side remark. We soon get back to it. And we would like to characterize, so this, we would like to characterize this subset of the set of all divisors that we care mostly about. I mean, this is divisors of rational functions. So one part, as we said before, we know that principal divisors have to have degree 0. I mean, degree is the sum of all the integer coefficients in a divisor. So if you want, you can think about it like this. We have an abelian group, divisors over E. And we have a map that I call degree that goes from this abelian group into the abelian group of integers that takes a divisor D, which is like sum NPP, and sends it to the sum of coefficients. And this is actually a group homomorphism. A group map. In fact, I have two group maps. One is from the divisors of E over K into the integers, and two from the divisors of E over K into the abelian, the elliptic curve group. And this I call sum. Sum is, I have D is some NP bracket P, and I send it to sum NP P. This is meaningful in the elliptic curve, right? Because you can always do integer times a point in the elliptic curve, and you can sum points in the elliptic curve. Okay, and this brings us to the main theorem that we worked quite a lot to prove, which is called Abel-Jacobi. And Abel-Jacobi says a divisor D is principal if and only if two conditions need to be met. One is that the degree of D is 0, and two, that the sum of D is 0, is O. And the important part here, there is if and only if. It means that if I can now cook a rational function, now, moreover, any two rational functions say R and R prime, such that the divisor of R is equal to the divisor of R prime, satisfy R equals C times R prime for some C in the field K. Okay, so this is a very strong result, and this summarizes a big portion of what we did on elliptic curves, and is then becomes very useful in later in the construction of the Weyl pairing and so on. But it's important that you understand the formulation. Okay, it really it's not hard to remember, I think, and it really plays a pivotal role. Any questions about this? Okay, just this is jumping a little bit back. I mean, there is this issue of a kind of calculus of divisors. That is, I mean, if I have it's an effect of principal divisors. I mean, if I have two rational functions, R and R prime, I can look at them in as two functions from E of k to the projective line. And in the projective line, I can, I mean, the projective line is just a k plus some additional point, infinity. So let's say if P is on E of k, such that R of P and R prime of P are not zero or infinity, are not, well, I can, there is a slightly more precise formulation, but let's say this will definitely be true, then I can do, I mean, R and R prime are like algebraic objects, right? It's like they are quotients of polynomials. So I can always multiply R and R prime. This is an element in the field of rational functions. But I can also take R of P, this is an element in the field K, and I take R prime of P, and I multiply them, and I claim that this is equal to R of, sorry, to this algebraic object, R times R prime, and then evaluated at P. Okay, and this, like a recurring theme in all this course, is that you can multiply infinity with infinity, you can multiply zero with zero, but we don't have a consistent way of multiplying zero with infinity. So, in fact, RP and R prime P could be zero or infinity, but I cannot have this result, this equality, if one of them is zero, if, like, let's say RP is zero and R prime P is infinity, then it's going to be an issue. But using this result, we can deduce a kind of a calculus of divisors, namely that the divisor of a product is the sum of divisors. And the divisor of a quotient, if this quotient is well defined, I mean, if R prime is not the zero rational function, this is the difference of the divisors. And divisor of constant times R is just the divisor of R. Okay, so these kind of results allow us to manipulate, and we used it in the, I think in the maybe even in the construction of the Weyl pairing, but definitely in the proof of its properties. Okay, so this was Abel Jacobi, and then the next big thing that we did was identifying torsion points. So but before I move to this, any questions about, is this covering the issues you had with the divisors?
Yeah,
Yes.
it's very, very nice.
Thank you very much. Yes.
Okay, and okay, and so we arrived to this issue of the last ingredient, basically, in order to do the Weyl pairing, is to identify the n torsion points. So I remind you, E of n is the collection of all points on the curve, such that NP is equal to O. So it's like, it's not exactly points of order n, because order is like, order of a point in an abelian group is the minimal number such that if you add this point to itself, you get 0. But here, it could be that let's say n is equal to 2k. So it could be that n is equal to 2k, and 2p is already 0, which means, of course, that np is going to be 0, and this means that p is a point of order of, is an n torsion point, but the order of p is not n. The order of p in the group E of k is going to be 2. So it's like a generalization of order. It's like all the points that get nullified by multiplication by n. And we already had, I mean, when we discussed points of order 2, I mean, when n is prime, n torsion points and points of order n are the same. The difference could be when n is not a prime. So when we talked about points of order 2, it's also 2 torsion points, but it's not, but it's because 2 is a prime. But more generally, we want to understand E of n, and we already know that E of 2, this is always, in fact, it's very easy to check that this is a subgroup of E of k bar. I mean, because if you take 2 points of, 2 n torsion points, P and Q, and you add them just like you add in the elliptic curve, and then you multiply by n, then you get np plus nq, and this is O. So also P plus Q is going to be an n torsion point, and similarly, minus P and minus Q are going to be n torsion points. So this is in fact a subgroup of the elliptic curve, I mean the k bar rational points of E. And as a sub, I mean, since it is a subgroup is a group in its own right, we know the number of points, of order 2 or 2 torsion points, we know them to be 4, right? This is like the point at infinity plus 3 others, let's say P1, P2, P3. And we know that E2 has a group structure. So if I do P1 plus P2, I get something. Either I get O or I get P3 or something. I mean, something within this group. And so I would like to say what is the isomorphism type of this group E2. And it was not hard to see that E2 has to be isomorphic as a group to Z modulo 2 direct sum Z modulo 2. This is basically because there are only two groups of order, of size 4. There is integers modulo 4 and this guy. This is called the Klein group. And in integers modulo 4, I have an element of order 4, namely 1. I mean, if you do 1 plus 1 plus 1 4 times, you get 0. And in E2, I don't have an element of order 4. All the elements are of order 2. So the only way, E2 has to be isomorphic to a group that has that all its elements are of order 2, and that must be the Klein group. It cannot be integers modulo 4. Okay, but that's like a baby case. That's easy. And we want, the big theorem here is that E of n is isomorphic to integers modulo n direct sum integers modulo n. I forgot to mention again this issue with algebraic closure. E of n is intentionally defined even if k is not equal to, if k is not algebraically closed, the n torsion points are always defined as the points in the k bar rational points. Okay, and then this theorem is always true. But in order to prove this theorem, we need to analyze, well, first, stepping stones. One is to analyze, so I have the multiplication by n map. This goes from EK to EK. And this, P, of course, goes to NP. And we basically want the kernel, E of n is going to be the kernel of this map, right? It's like the points in EK such that NP is equal to 0. But this is a new creature. It's like mapping from the points from the k rational points to the k rational points, and in a polynomial way, because we know that the addition, the group law of on the elliptic curve is constructed by polynomials or quotients of polynomials. So we needed a notion of a rational map. Rational map, it means that let's say rho from E to E. It doesn't have to be from E to E, it could be from E to E prime, but in our case we only care about rational maps between the curve to itself. Let's say the curve has the equation y squared equals x cubed plus ax plus b. Then rho is like a pair of rational functions. So R comma S, where R and S are rational functions on E. So R and S in particular can be regarded or can be viewed as functions from E of K to the projective line. So K union infinity. And what I want from rho is that it is defined over some field K, and I want for any extension, let's say L of K, and any point on the curve, let's say this point is A comma B, and it is on the curve over L. It's like an L rational point. Then I can plug in P into R, and I can plug in P into S, right? Because R and S, each of them has two variables. So I have RAB, I just write RP. This is and I have a S of P. Each of these guys is an element in the projective line. And this, I think of it as like the X coordinate, and this is the Y coordinate. And in order, I want that RP, SP will belong to E of L. So I want rho to map points in E of L to points in E of L. And the only way to guarantee it, I mean, what does it mean to be a point in E of L? It means that if I take the Y coordinate and square it, I get the same thing as if I cube the X coordinate and I add A times the X coordinate and I add the constant B. So I want that SP square would be equal to RP cubed plus ARP plus B. Okay, and then I am guaranteed that rho induces a function from E of L to E of L for any extension L. And again, this any extension is important because I might not start with an algebraically closed field, like this K could be FP, and I would like to consider the algebraic closure of the field I started. So whatever equations I want to be satisfied, I want it to be satisfied over all extensions. And there is a main example of this. This is, I mean, a multiplication by n is a rational map. I can think of it going from E to E. So for any field that you put I mean, that contains the field in which E is defined. Any extension of it, I can do multiplication by n. And this is, so e.g., a multiplication by n is rational. Any questions, Nicholas or anybody else? Okay, and so then multiplication by n, in particular, it has two coordinates. This, we denote them gn and hn. And we went about analyzing the z. So each of these guys, gn, for example, is going to be a rational function on E. As a rational function, it has zeros and poles, right? So we went about analyzing the zeros and the poles of these coordinate functions of multiplication by n in order to eventually understand multiplication by n. And this became an interesting mix of techniques because we had what was it? How's it called? Recurrence relations. So we analyzed Gn and Hn, and eventually we had a theorem that identifies the divisor of Gm minus Gn. This was in terms of Em and En, and I think well Em minus n and so on. But this whole thing, well, again, I forgot to ask another detail. This theorem is only true if the GCD of P and N is 1. I mean, if P does not divide N, basically. And if P divides N, then it becomes something else. It's a mess. We didn't touch it at all because we don't need it. I mean, in the construction of the Weyl pairing, we always assume that the prime does not divide the n in the n torsion points. And P here is the characteristic of the ground field. Okay, so and this, of course, this propagates into this theorem. So P does not divide n. Otherwise, we don't know. But using this, we recovered another stepping stone that the number of points on En is n squared. And then using we had an argument using the classification of finite abelian groups that says that En is isomorphic to Zn sum Zn. And okay, and that led us to the Weyl pairing. But I think I want to leave a little bit of room to kind of open discussion or questions. So I will not review the Weyl pairing.
So one question: this last thing is the same result that we got like some minutes ago when you were talking about the n torsion points, right?
Can you say again?
Yeah, so this last thing about like the group of the n torsion points of the elliptic curve being isomorphic to Zn plus Zn. It's like we got this result here, but like a few minutes ago, you also got the same result when you were doing the n torsion point stuff.
Yeah, I mean, I guess I wrote it in the beginning just to indicate what is, where are we going.
Okay.
This was like a big. This was set as a big goal.
Okay.
In some point, and then we had stepping stones to it.
Okay, I see.
Okay.
Thanks. Yeah.
So, I mean, the way here, if you remember, to prove that the number of points of En is n squared, this was recurrence relations. And after we knew that this is n squared, then we used the classification of abelian groups and some basic properties of En, because we know that En, for example, it cannot be Z modulo n square, because in Z modulo n square we have an element of order n square, right? And in En, all the elements have order at most n. Other questions?
If we have an offline meeting in DEF CON, maybe we could review then the well pairings there and the Miller algorithm, because I missed last session because we had an AdSec thing, and I looked through the Miller algorithm on my own, and I kind of I technically understand what it does, but I didn't get any idea why it looks like that.
Okay, yeah, sure. We can talk about it.
I tried to Google something like, I don't know, video, like YouTube video or articles, but no one explains it.
Yeah, so I will explain. It's not a big deal. Yeah, but I guess, I mean, it's not going to be today. We ran out of time. Other requests, I mean, for DevCon or otherwise? Then thank you all for staying this long with the course, and yeah, see you around.
Thank you very much.
So much. Thanks a lot.
It was incredibly cool. It was incredibly cool.
Thank you.
Yeah.
Thanks a lot.
See you in person then.
Yeah.
Yeah,
Bye-bye.
see you in DEF CON. Bye.
Bye. Thank you again.